Hello, hello! Alright, so this is the next in the installment of going through solutions to some of these things that were on that most recent benchmark. This particular video, we're going to talk about monotone convergence. So, there's a statement we want to prove. Let me hit this button so it stops going out of focus. Let an be given by, and then there's our occurrence relation specified. A1 equals 1, an plus 1 equals an over absolute an plus 1. Show an converges using monotone convergence. So we know what we need to do here, right? We need to show that this sequence is monotone and bounded in the right direction, depending on whether it's increasing or decreasing. So let's just build some intuition first. So this is just scratch work. This isn't anything that you would turn in. Let's see, so A1 is 1, A2 is A1 divided by A1 plus 1, so that's 1 divided by 1 plus 1, that's 1 over 2. It seems to be decreasing. We need the sucker to be decreasing and bounded below. So let's do decreasing first. To do that, we need an plus 1 less than or equal to an. Well, we have our occurrence relation, so let's use that. And again, this is all scratch work, so this can be really messy. That's an divided by absolute an plus 1. There's what we want. Alright. Well, let's see. This looks like a denominator that is bigger than 1. So this thing, an divided by an plus 1, is less than an divided by 0 plus 1. Yeah, that's an. And I guess there's secretly an assumption here. We need an to be bigger than 0 for that to work. Alright, so this also suggests that maybe there's a bound we could get. Let's try to get that bound. Alright, so that means we need, let's see, this is our occurrence relation. When you're working with occurrence relations, probably 1 induction. A1, that's bigger than 0 because this is 1. So there's like a base case that we'll write down. An plus 1, that's an divided by absolute an plus 1. That thing is bigger than 0 by the inductive assumption, which we haven't written down, and that certainly is bigger than or equal to 1. Yeah, that's bigger than 0. Alright, so let's do that. So it looks like we need this to make that walk, so we should do the boundedness first. Alright, so, proof. First, we show an is bounded below by 0. Let's proceed by induction. Base case. When n equals 1, a1 equals 1, which is bigger than 0. So, an is bigger than 0 at least when n equals 1. Inductive step. We get to fix some n in the natural numbers, and we get to assume an is bigger than 0 just because that'll line up with this inequality, and in the scratch walk it seemed the strict inequality is what we got. Then an plus 1 is equal to an divided by absolute an plus 1 by the recurrence relation. Let's see. As an is bigger than 0 by the inductive assumption. You know what? Let's maybe even be extra careful that you can figure out what you mean by the inductive assumption. I'll label it with a star. There, that's now labeled with a star. Also, absolute an plus 1 is bigger than or equal to 1 because it's absolute value of something plus 1. So, an plus 1 equals an divided by absolute an plus 1 is bigger than 0. This completes the inductive step. So an is bigger than 0 for all n. Finally, we show an is decreasing. That's illegible. An is decreasing. For any n in n, an plus 1 equals an divided by absolute an plus 1 is less than an, let's say less than or equal to, as absolute an is bigger than or equal to 0. I guess those could be strict inequalities too, but you don't need that to get just decreasing. Thus, an is decreasing. So by monotone convergence, as an is decreasing and bounded below by 0, an converges. Notice this doesn't tell you what the limit is. In fact, because I saw some clever write-ups that did something sneaky, I'm also going to give a different approach. So this is a complete proof. This is the proof I was looking for. Here is a different proof. So let's let an be given by a1 equal to 1 and an plus 1 equals 1 over absolute an plus 1 an divided by absolute an plus 1. So here's the thing you can think about whenever you have a recurrence relation. You can try to solve it. And to do that, we'll try to notice a pattern. If we can notice a pattern that looks like a formula we can prove, we can try to prove it using induction. So let's see. a1 equals 1. a2, as we've already established, is 1 over 1 plus 1 is 1/2. a3 is a2, 1/2, divided by absolute value of 1/2 is just 1/2 plus 1. All right, so let's see, that's 1/2 divided by 3/2, that looks like 1/3. a4 is 1/3 divided by 1/3 plus 1. It's 1 over 3 divided by, 4 over 3. That's a quarter. I think we notice a pattern. Maybe an is just 1 over n. The way you would show this. And this is nice because 1 over n converges. It converges to 0. Let's try to proceed by induction to show this. So you fix some an, you get to assume an equals 1 over n for some fixed n. Then an plus 1. So it's an divided by absolute an plus 1. That's 1 over n divided by 1 over n is positive, so the absolute value values don't actually matter. 1 over n plus 1. That's 1 over n divided by 1 plus n all over n. Yeah, that's 1 over n plus 1. There's the inductive step done. So, let's use this idea instead. Oh, I should finish the statement. Show an converges. Proof. We will first show that an equals 1 over n for all n. Proceed by induction. When n is 1, a1 equals 1, while 1 over 1 equals 1, so an equals 1 over n at least when n equals 1. This completes the base case. Now we do the inductive step. We now fix some n in n, and we assume an equals 1 over n. Then an plus 1 is equal to an divided by absolute value an plus 1 by the occurrence relation. Equals 1 over n divided by 1 over n plus 1 by the inductive assumption that an equals 1 over n equals, and I don't need to see the algebra, right? I know you know how to simplify fractions. 1 over n plus 1 by simplifying fractions. This completes the inductive step. Thus, an equals 1 over n for all n, and as a consequence, an converges to limit 1 over n, which we have established already, is 0. Cool. So here are two different proofs that you can use on this one. One of them was the one I was intending. Right? Generally, you can't solve most occurrence relations, but when you can just use the solution to prove things about them. Neato. Cool. So that completes the monotone convergence proof. The only one left on the list to do is cardinality. That'll happen in a moment. Talk to you soon.